Here are the prime numbers as they come: 2, 3, 5, 7, 11, 13. And watch only the very last digit of each one as they go by. 2 ends in 2, 5 ends in 5, and then something settles in. From 7 onward, every prime on the list ends in 1, 3, 7, or 9, and it never once steps outside those 4. That is not a coincidence you have to take on faith. The number ending in 0, 2, 4, 6, or 8 is even, so the only even prime is 2 itself. A number ending in 5 is a multiple of 5, so the only prime there is 5. Strip those away and every other prime, all the way out, has to land on one of just 4 endings. So the whole infinite supply of primes, past the first 2, gets sorted into 4 buckets by its last digit. And once you see the 4 buckets, a plain question almost asks itself. Each bucket is catching primes as we climb. Does any one of them ever stop catching them? Could the primes that end in 7, say, simply run out at some point, while the other 3 carry on? Settling that, for every bucket at once, is what this whole video is about. To get a grip on one bucket, line its numbers up in order, because the bucket of last digit 7s is really a simple sequence in disguise. Start at 7 and add 10 over and over. 7, 17, 27, 37, 47, and on forever. Every number ending in 7 appears exactly once in order. Now mark the primes among them. 7 is prime, 17 is prime, 27 is 3 times 9, so it is out. 37 prime, 47 prime. Skip a few, and you get 67, 97, 107, 127 all prime. The primes keep showing up, with composites scattered in between, as far as anyone has cared to check. A sequence built by starting somewhere and adding the same step each time has a name worth saying once. It is an arithmetic progression. 7, then plus 10, plus 10, plus 10. And the question from a moment ago is now sharp. This progression clearly starts off rich with primes. Does it stay that way? Is there a last prime ending in 7, after which the sequence is all composites the rest of the way to infinity? The honest answer is that no amount of checking can settle it, because the sequence never ends, and there is always more of it past wherever you stopped. We need a reason, not a search. Before reaching for the answer, notice that you cannot ask this of just any sequence, because some progressions obviously hold almost no primes at all. Suppose you start at 3 and add 9 each time. 3, 12, 21, 30, 39. Every single term is a multiple of 3, because you began at a multiple of 3 and kept adding 1. So apart from 3 itself, not one of them can be prime, ever. The same goes for starting at 2 and stepping by 4. 2, 6, 10, 14, all even, prime only at the very start. The trouble is plain. When the starting number and the step share a common factor, every term inherits that factor, and the progression is dead for primes after at most 1. So there is one thing a progression must have if it is to stand any chance. The start and the step have to be coprime, sharing no factor bigger than 1. 7 and 10 are coprime, so that sequence is allowed. 3 and 9 are not, so it is ruled out. And here is the claim the whole video is built around, settled in 1837 by a mathematician named Dirichlet. That single condition is not just necessary, it is enough. Every arithmetic progression whose start and step are coprime contains infinitely many primes. No exceptions for any allowed start, for any step. That claim covers infinitely many progressions at once, which sounds like it would need heavy machinery. For a few special cases though, you can prove it sitting down with a pencil, using a trick 2,000 years old. Look at the primes that leave a remainder of 3 when you divide by 4. 3, 7, 11, 19, 23, 31. Suppose, just to try it, that this list someday stops, so you can write down all of them. Multiply your whole finite list together, multiply that by 4, and subtract 1. Take the small list of just 3 and 7. 4 times 3 times 7 is 84, and 1 less is 83. Now look at what 83 has to be. It is 1 less than a multiple of 4, so it leaves a remainder of 3, just like the primes we are hunting. Divide it by 3, or by 7, the primes we used, and a remainder is left over, so neither one is a factor. And here is the quiet engine of the whole thing. A number that leaves remainder 3 can't be built only from primes that leave remainder 1, because multiplying remainder 1 numbers together only ever gives you remainder 1 again. So 83 must contain a prime that leaves remainder 3, and it is a new one missing from our list. We assumed the list was complete, and it handed us a prime it did not have. The list can never be complete. That argument is clean and it is airtight, so it is tempting to think you could repeat it for every bucket. The moment you try, it falls apart. And the way it falls apart is the whole reason the real proof had to be invented. The result of the trick does not even need to be prime, by the way. Take 3, 7, and 11. 4 times their product, minus 1, is 923, and that is not prime. It splits into 13 times 71, but 71 still leaves a remainder of 3, and it is still new, so the argument lives. We never needed a prime, only a new prime factor of the right kind. Now try the same move on the primes that leave remainder 1, the 5s and 13s and 17s, and the engine seizes up. Multiplying remainder 1 numbers gives remainder 1, which tells you nothing about where a new factor hides. You need an entirely different idea for that bucket. As it happens, there is a separate trick, leaning on the fact that any odd prime dividing a square plus 1, like 100 for 101, must leave remainder 1. But that trick is special too. Every bucket, for every step, would need its own clever hand-built argument, and nobody had one that worked for all of them at once. The pencil gets you a handful of cases and then stops cold. So Dirichlet did something that had never been done for a question about whole numbers. He answered it with calculus, with infinite sums and the smooth machinery of analysis. And that move is what makes him the start of a whole branch of the subject. The idea begins by tagging the numbers. Instead of treating a bucket as a yes or no membership, he attached a value to every whole number, plus 1 or minus 1, in a repeating pattern keyed to the step. For the step of 4, the pattern is simple. Numbers that leave remainder 1 get a plus 1. Numbers that leave remainder 3 get a minus 1. And the even numbers in between get a 0. This repeating sign pattern has a name, a character. Then he fed those tags into an infinite sum, 1 over each whole number, but with the sign the character assigns. For this pattern, you get 1 minus a third plus a fifth minus a seventh, and onward through the odd numbers. A sum like that, built from a character, is what we now call an L function. What matters is that the same sum can be rewritten as a product running over the primes alone. So this one tidy expression secretly carries information about every prime and which bucket it falls in. That hidden link between a sum over all numbers and a product over the primes is the door Dirichlet walked through. With the L functions built, the entire proof comes down to a single fact about them, and it is the hard, deep part that took real work. The sum must not equal 0. Watch why it matters on the sum we just wrote. 1 minus a third plus a fifth minus a seventh, on through the odd numbers. Add the terms up and the running total bounces, then closes in. 1, then 2/3, then about 0.87, then 0.72, tightening toward a single value near 0.79. That value is exactly pi over 4. It is some distinct positive number comfortably away from 0. Here is what that buys. If you take logarithms of the product over primes form, the primes in each bucket get pulled apart into their own running total. Should the L function ever sink to 0, those totals could cancel and stay finite, which would let a bucket quietly dry up. Because the value sits away from 0 instead, the cancellation cannot happen, and the primes in that bucket are forced to go on without end. Strictly speaking, proving the sum avoids 0 for every character, including trickier ones than this, is the genuinely difficult step, and walking through all of it would be its own video. The shape of the argument, though, is exactly this: one non-zero number per bucket, and the infinitude follows. Dirichlet's method gives back more than a yes. It says the primes do not just keep coming in every bucket, they are shared out evenly between the buckets, and that opens a genuinely surprising door. Go back to the 4 last digit buckets, 1, 3, 7, and 9. Count the primes up to 1,000,000 in each. The bucket ending in 1 holds 19,617 of them. ending in 3, 19,665, ending in 7, 19,621, ending in 9, 19,593. 4 counts, all within a hair of one another, each a quarter of the whole. In general, for a step with some number of allowed buckets, every bucket collects the very same share. Now the surprise, and it is a real one. Even when the final shares are equal, the race to get there is not a tie at every moment. Split the primes by remainder after dividing by 4 into the 1s and the 3s, and the 3s pull ahead early and stay ahead for a startlingly long way. Up to 10,000, the 3s lead the 1s by 10. They keep that lead, prime after prime, until you reach 26,861, which is the very first place the 1s finally edge in front by a single prime. Chebyshev noticed this lean back in 1853. The destination is dead even, and the run there leans the whole way. So that is the whole shape of it. Sort the primes by their last digit, and they fall into a handful of buckets. Line one bucket up, and it is an arithmetic progression, a start and a fixed step. As long as the start and step share no common factor, that progression holds infinitely many primes, and the proof for a few buckets is a 2,000-year-old pencil trick. For all the buckets at once, Dirichlet reached for infinite sums, attached a sign pattern to the numbers, and rested everything on the one fact that those sums never fall to zero. It was the first time a question about plain whole numbers was cracked open with the tools of calculus, and it started the field we now call analytic number theory. Peter Gustav Lejeune Dirichlet wrote it down in 1837. The chair he later held at Göttingen passed, after him, to Riemann. And that handoff is the open door. The even sharing of the primes and the strange lean in the race are the first hints of a far deeper pattern in how primes are spread out. The pattern that leads straight to Riemann and the most famous unsolved problem in the subject. That one is for another day. If there is one thing to carry away, it is that you can be certain an endless supply of primes hides inside a pattern, in every bucket the rules allow, without ever finding the end of a single one. A sign pattern, an infinite sum that refuses to vanish, and the primes are pinned down forever. This was one more in a series on how a single person settled one hard question. Stay for the rest.